Far beyond Neptune, something invisible is tugging on the solar system like a ghost with mass. Out in the deep freeze, thousands of icy worlds move in slow, predictable orbits. But a handful of them don't behave. Their paths are tilted, stretched and mysteriously aligned, as if an unseen giant were herding them along. When astronomers ran the numbers, the best explanation was shocking. A planet perhaps 10 times Earth's mass, orbiting so far away that one year they could last more than 10,000 of ours. We've never seen it. We don't know exactly where it is. But its gravitational fingerprints might already be written across the outer solar system. To understand Planet 9, you first need to know how far really is. Neptune, the outermost known planet, orbits at about 30 astronomical units from the Sun, 30 times farther than Earth. Pluto averages about 39. Beyond that lies the Kuiper Belt, a vast ring of icy debris stretching from roughly 30 to 50 astronomical units. These objects obey the gravity of the known planets and the Sun, and their orbits look fairly random in orientation. But then, astronomers started finding extreme trans-Neptunian objects, bodies with orbits that stretch hundreds of astronomical units from the Sun, taking thousands of years to complete a single loop. These orbits weren't random. Their closest approach points, their perihelia, seemed clustered in space, like compass needles all pointing roughly the same way. That's not what you expect from chaos. That's what you expect from a shepherd. In 2016, planetary scientists Konstantin Batygin and Mike Brown took this weird clustering seriously. They asked, if gravity is the only game in town, what kind of hidden mass could sculpt orbits like these? They ran thousands of numerical simulations, letting a hypothetical planet tug on a population of distant icy bodies over billions of years. When they gave this planet a mass around 5 to 10 Earths, on an elongated orbit tilted about 20 degrees to the plane of the known planets, something remarkable happened. The simulated objects began to match reality. Their perihelia clustered, their orbits tilted in similar directions. Some were even flipped into retrograde orbits, circling the Sun backwards, just like a few real objects we found. From this, they inferred a candidate, Planet 9, perhaps 10 Earth masses, orbiting at a distance of 400 to 800 astronomical units, with a year lasting between 10 and 20,000 Earth years. So how can a planet we've never seen be so influential? Gravity doesn't care about brightness, it only cares about mass and distance. Imagine the outer solar system as a slow-motion billiards table. Every orbiting body feels tiny gravitational nudges from every other, but a massive planet, even very far away, can gradually reshape orbits over millions of years. Planet 9's proposed orbit is highly eccentric, more like a stretched ellipse than a circle. At its closest, it might approach a few hundred astronomical units from the Sun. At its farthest, it could drift thousands of astronomical units into the dark. As it moves, its gravity can trap smaller icy bodies into resonances, where their orbital periods form simple ratios with the planets. Over time, these resonances herd objects into preferred orientations and inclinations, producing the strange clustering we observe today. The evidence for Planet 9 is entirely gravitational and statistical. No telescope has captured its reflected light. Instead, astronomers are reading the outer solar system like a crime scene. First, there's the alignment of those extreme trans-Neptunian objects. Their elongated orbits all point roughly the same way in space, and their orbital planes are similarly tilted. Random chance could do this, but the odds are low. Estimates suggest less than 1% if no hidden planet exists. Second, there's the existence of highly inclined and even retrograde objects in the Kuiper Belt, like the dwarf planet candidate 2015 BP 519. Its orbit is so tilted that it's hard to explain with just the known planets. Simulations show that a distant massive planet naturally pumps up inclinations like this. Third, Planet 9 could also help explain why the entire plane of the solar system is slightly tilted, about 6 degrees, relative to the Sun's equator, by acting as a distant gravitational torque over billions of years. If Planet 9 is real, what kind of world is it? The leading idea is that it's a mini Neptune, a rocky and icy core wrapped in a thick envelope of hydrogen and helium. similar to Uranus and Neptune but smaller. With a mass around 10 Earths, it would be too big to be a typical rocky super-Earth, yet too small to be a gas giant. Its surface, if it has one, would be unimaginably cold, perhaps 30 to 50 Kelvin, just a few dozen degrees above absolute zero. Sunlight out there is thousands of times weaker than on Earth. Noon would look like deep twilight. Another possibility is that Planet 9 is a captured rogue planet, a world formed around another star and later stolen by the Sun's gravity during a close encounter in the early cluster where our Sun was born. That's speculative, but dynamically possible. Finding it is brutally hard. At hundreds of astronomical units, even a Neptune-sized planet would be incredibly faint, reflecting only a tiny fraction of the weak sunlight it receives. It would move slowly against the background stars, shifting its position by maybe a few arc-seconds per year, a tiny crawl on the sky. Search teams use wide-field telescopes, like the Subaru telescope in Hawaii, taking repeated deep images of the same patches of sky months apart, then using software to hunt for objects that move. The parameter space is huge. Planet 9 could be anywhere along its orbit, and if it's near aphelion, its farthest point from the Sun, it would be at its faintest. Upcoming instruments like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will repeatedly scan the sky with unprecedented depth, potentially revealing Planet 9 or ruling out much of the space where it could hide. If Planet 9 exists, it reshapes our understanding of the solar system's architecture. First, it would mean the Sun's planetary system is even more extended than we thought, with a massive world acting as an inner guardian to the distant Oort cloud, the reservoir of long-period comets. Planet 9's gravity could perturb comets and icy bodies, occasionally nudging them inward toward the inner solar system, subtly influencing impact rates over geological timescales. It might also help explain the origin of some unusual comets with strange orbits. On a broader scale, Planet 9 would show that our system fits better with what we see around other stars. Many exoplanetary systems host super-Earths and mini-Neptunes in various configurations. Having one of these worlds lurking in our own backyard, relatively speaking, would make the solar system feel less like an oddball and more like part of a cosmic pattern. But there's a real possibility that Planet 9 doesn't exist. The observed clustering might be an artifact of small number statistics. We've only discovered a few dozen extreme objects, and our surveys don't cover the sky uniformly. Maybe we're just more likely to find objects in certain regions, creating a fake pattern. Alternative explanations include collective gravity from many smaller bodies, a kind of gravitational average of a massive unseen disk of icy objects, or past encounters with passing stars that stirred up the outer solar system long ago. Right now, the Planet 9 hypothesis is a well-motivated, testable idea, not a confirmed discovery. The next decade of sky surveys will either tighten the noose around its predicted position or show that the evidence evaporates with better data. The most important open question is simple and profound. Is there actually a ninth planet shaping the outskirts of our solar system, or are we seeing patterns in noise and gaps in our surveys? Answering it will demand patience, better telescopes, and a willingness to be wrong. If Planet 9 is found, it will be the first new major planet added to the solar system since Neptune in 1846, and the closest alien world we can never visit easily. If it isn't, we'll still have learned something deep about how to read the faint gravitational handwriting at the edge of the Sun's domain. And that's exactly the kind of mystery we love to explore here on Terra Nova.